So good afternoon. Good to see everybody here. Quick review of what it was we were working on. We're solving problems where you have something that you need to optimize. It could be that it's area and you want the area to be as large as possible. For some reason, it could be that it's area, and I'm sure you can come up with a scenario, you want the area to be as small as possible for some particular reason. Maybe because less area means less cost for painting it. I don't know. But the bottom line is you have some quantity that needs to be optimized. Your job is to, in order to find out where that happens, is to imagine a graph. I mean, I'm not saying you have to physically sit there and think about this and imagine it, but you have to be able to find the connection between this function we're talking about and this variable, which I'm going to call O, that you want to optimize. If you want to optimize it to make it as large as possible, you need to look at it as a function of some other variable. You don't do it graphically. This other variable could be anything. I'm just going to say v for variable. So what you end up with here is a function, O, the thing to be optimized is a function of v, and perhaps the function looks like that. Again, you don't have to graph it. I'm saying that if you did graph it, it looked like that. Well, that happens to have a point that corresponds to a maximum value of O, and it also happens to have a point that corresponds to a minimum value of O. And we're going to see a question eventually, probably tomorrow, where the problem, in fact, is going to have two answers. It will be how to cut a piece of wire in some way to create two shapes that have the most area, and how would you cut it so that you have two shapes that have the least area. But the bottom line is both of these points correspond to critical values of x, well, critical values of v, but you get my drift. So once you have that function, you differentiate the equation with respect to the other variable. In other words, what you would want to do if you're looking at this particular relationship is you would want to find dO, dV, and then find the critical values of that derivative, because that will be where the derivative is either 0 or undefined, which corresponds to max-min points. I had mentioned to you yesterday near the end of the class, I believe, that values of V are critical if the numerator is equal to 0, and also they're critical if the denominator is equal to 0. You get my abbreviated notation here of what I'm talking about. But I had mentioned yesterday that until we get a little bit deeper into this whole bit of business, it will always be, well, I've always struggled with this. It's always going to be that until we encounter a case where it's not. Sooner or later, I'm going to say to you, you know what? I think the denominator being equal to 0 gives us the proper solution here. So most times, let's just continue with this. So you determine the critical numbers, and then you have to determine which of the critical numbers correspond to the solution. And I've got in brackets, look at the domain and or the first derivative chart. At least 9 times out of 10, when you look at the domain and you take all your critical numbers and you start getting rid of the critical numbers that are not in the domain, most of the time you're left with one critical number. And a lot of the time you only have one critical number to begin with. So it's going to be very rare that you need to complete a first derivative chart to answer these questions. In a post-secondary setting, you might be required to do a first derivative chart to confirm that that only critical number does in fact correspond to a maximum or to a minimum or whatever the case is. I think that's it. Now, when we last met, we finished off the examples. I gave you the two solutions. I said for the last two, I think 3 and 4, I gave you the answers. And then I said, what you're working on are these problems. And I don't know how far you got, whether you worked on it at home or not. I don't know if you have any questions or not. But between today and tomorrow, at a minimum, we're going to be doing calculus. We're going to be practicing. We're going to be learning math. And a big part of learning, and you're going to discover this a lot in 30-1 over the coming week, a big part of you learning is sometimes watching me do problems. So with that said, does anybody have any questions from this list you would like me to go over? Yep.
Number 6 on 199. Number 6 on 199.
Okay. On 188?
199.
Okay. So this is a classic kind of cost-revenue situation. An apple orchard currently has 80 trees planted per hectare. I don't even know how big a hectare is. I probably should, but it's a plot of land. And the average yield is 400 apples per tree. For each additional tree planted, you drop by 4 apples on average. So you may not think, well, that's not a lot, but you're talking about 80 trees, so it adds up, right? And again, the biological and physical reason for that and chemical reason is planting more trees takes the fixed amount of nutrients available in the soil and dilutes it, thins it out per tree. It might be that in reality you get the same number of apples, they're just smaller or not as good. How many trees per hectare will give the largest crop? So the total number of apples will be equal to the number of trees multiplied by the number of apples per tree, right? So as it stands right now, if you take 80 trees times 400 apples per tree and get 32,000, I think would be what it would be, you'd get 32,000 apples in the growing season. But if and there's no need to do this, but I just want to make sure that you understand what's happening here. If there are 80 trees, you get 32,000 apples, right? If you were to plant, I don't know, I'm going to go in total 85 trees. We have to do a little bit of problem solving here. You've planted an additional 5 trees, and you're losing 4 apples per tree. So by my count, and it's late in the day, I admit, but I think we lose 20 apples per tree. That would mean we would take 85 times 380. And get 32,300. And to the less informed or thoughtful person, you might think, oh, I'm just going to keep planting more and more trees and getting more and more apples because the number of apples went up. But, and I'm going to have to grab my calculator for this one. I mean, if we planted 160 trees, we've increased by 80 trees, and each tree is 4 apples less. We've lost 320 apples per tree. Okay, good. So that would be 160 trees times we've lost 320, which only leaves 80 apples per tree. I think that that is 14,400, but I'm probably off. 14,600? 12,800? Okay. So, and again, you're not doing this. I'm taking the opportunity to explain to you the mathematics of what's going on, that initially what happens is you plant more trees, you get more apples, but then it tapers off at some point and starts going in the wrong direction. So, you know, this is more apples than 80, and this is more apples than 160 in terms of trees. That's the problem. And I know I didn't need to explain that to you, but I wanted to anyway. So how do we define the other variable here? We need the other variable. I'm going to use t as the extra number of trees. Okay. So the number of trees you're going to plant then will be the original 80 plus however many additional trees you plant. The number of apples per tree is going to be the 400 minus 4 apples for every additional tree is minus 4t. So this is the function that we would use. Does that make sense? This is the function that we would use in order to find out the maximum n. When I expand this out, because of course I'm going to have to find a derivative, I get negative 4t squared, which is a really good thing at this point because that tells you it's going to be a parabola. Well, that will be the highest degree when you expand it out. It will be a parabola that opens down, which means there will be a maximum. What do I get? For the outer, I have negative 320, and for the inner, I have 400. These are both t's. Can you check my arithmetic with the numbers there? Not feeling a lot of confidence coming back my way. 400t, negative 320t. Actually, I think it's right. I think that's okay. So now we're ready to move on to the next level here, or stage. dn dt equals negative 8t plus 80. You know, I'm just thinking about something here. I've told you again and again and again, I don't think it's a good idea to write equals 0. But, I mean, is it wrong? Is it wrong to say that since this is a linear derivative, the only critical number will be where it's equal to 0? No, you can solve that. I think a more sophisticated approach, a more less high school approach is to factor things and say that the critical value of x is the one that makes that factor 0, which means 10. So what that's telling us, Jay, is that in order to get the most apples, you need to plant 10 additional trees. Right? So, and again, this is, if the question just says how many trees should be planted, well, I think this is not ambiguous. How many trees per acre, per hectare will give the largest crop? 90. If it just said how many trees should be planted, it's maybe like, what do you mean, extra trees planted? Because we already have 80 planted. But I would never try to steer you wrong that way. I'd never try to trick you by using weird language. In other words, on an exam, a numerical response question would probably say, how many additional trees does this person need to plant per hectare? Is that okay? Okay. Any other questions? Okay, I feel as though I want to move on, and I know that you haven't completed all of these problems, but I want to move on and do one more example today. Okay. And this is example number 4. It's the soup can problem, which is a classic kind of problem. So a cylindrical can is to be designed, and it has to hold 384 milliliters of soup. That 384 milliliters is 384 cubic centimeters. So that's the volume. Now you're going to either need your formula sheet out for geometric figures or not. I guess it doesn't matter. I'm going to explain the formulas as I go through. There's 2 formulas that we're going to need here. One is for the surface area of a can. And the surface area of a can is what it is. And on your formula sheet, it might say 2 pi r squared plus 2 pi r h, or it might say 2 pi r h plus 2 pi r squared. It doesn't matter. But it is what it is, and I give you a formula sheet at this level, but post-secondary you might not. It is what it is because the can is composed of 3 faces. There's the lid, there's the base, and there's the wraparound, so to speak. And when you take a look at a can, it doesn't matter, a cylinder, no matter how tall or short it is, what you've got is for area a pi r squared for the top and a pi r squared for the bottom. So that's where that 2 pi r squared comes from. The 2 pi r h comes from the fact that if you were to cut the top and the bottom off and discard them, you would be left with a tube. You would be left with that, right? But a tube is a rectangle. All you have to do, and I used to actually have a can that I would cut up, and then one day I cut myself on it, and I thought that's not a good idea. You can cut the top and the bottom off of a can, and then with tin snips or some kind of cutters, you can cut along the side of the can, and you can unbend this into a rectangle. And when you do unbend it into a rectangle, what you are going to have is a rectangle where this was the circumference of the can. How many of you have seen this explanation before of the formula? Hopefully you have. Probably not in high school, but maybe junior high. And that means that this is a rectangle that's 2 pi r by the height of the can. So that's where the 2 pi r h comes from. So we're going to need that. And the reason why we need that, and I want to just rewrite this formula down here where I'm going to work with it. The reason why we need that is simple. Because we need a formula for something that we need to optimize. You're trying to minimize the cost of the can, right? If you read the question, it says, what dimensions will minimize the cost of materials? Well, I don't have a formula for cost, but I have a formula for the amount of materials, and it's reasonable to assume that more materials are more costful. Costful? Whatever. There is an oversimplification of the process in this example, and I'll come back to that idea a little bit later. But now here's a problem. We developed this formula, or use this formula, because you want to be able to imagine a graph that exists with area on the vertical axis and some other variable on the horizontal axis. The problem here is this is defining area as a function of 2 variables, which is not doable. You can't imagine a graph here because there's only 2 variables on this graph. Our equation has 3 variables. So we have to get rid of h or r. And the question is, how do we do that? Well, we go to the other formula, which is volume equals 1/3 pi r squared h, I believe. Any takers on that? You want to just look at your formula sheet? I'm pretty sure that's right. No. I'm thinking of a cone. Pi r squared h. Just pi r squared h. I don't know how a cone got in there. That's okay. Right? Well, that makes sense. And you should be able to come up with that on your own because that's a regular solid, right? If I take a look at a can, which is a cylinder, thought I had a can of soup. It has the same shape, that circle, all the way from the bottom to the top. So it's a regular solid. It's the area of the base, which is pi r squared times the height. And this pi r squared h is equal to 384, which is your equation of constraint. It doesn't matter how tall the can is or what the radius of the can is. They have to multiply together pi r squared h to give 384. Well, let's not nitpick. There's got to be a bit of error in there, and there's other issues, but actually there probably doesn't have to be error in there. I don't think we want error in there. So what are we going to do? We're going to rearrange this equation for one of these two variables so that we can get rid of that variable in the second equation that I have on the bottom left. I hope it's clear that rearranging for h is probably your wisest move. A couple of issues. If you rearrange that equation for r, you're going to have to take a square root, and then you're going to have to substitute it in twice. However, if you simply say that h is equal to 384 over pi r squared, no problem. This can go right there. And then we got the problem beat, at least in terms of the tough part, which is traditionally finding the equation in max-min problems. So area will be equal to pi r squared plus 2 pi r times h, which is 384 over pi r squared. I really hope that it's just become natural that any time, whether it's related rates or max-min, you develop your function that needs to be differentiated, that you say, can I simplify it to make my job easier, right? And, clearly we have pi on pi here in the second term. We have r on r squared. We've got 2 times 384. You're waiting for me to find that, I take it. 2 times 384. We can simplify all of that. And what we end up with is that the area, which is representative of the cost of the can, is pi r squared plus 768 r to the negative 1. You want to double check my math there with that last step? I think it's okay. I mean, I know it's fine except for the 2 times 384. Yeah.
There should be a 2 in the first part. It should be 2.
Oh, yeah, wow. There should be a 2 there. Thank you, Eli. 2 pi r squared plus 2 pi r h. So I went ahead and wrote r to the negative 1 because it's going to be simpler to differentiate that rather than saying over r. So we're just about home. dA dr is equal to 4 pi r minus 768 r to the negative 2. And there's a temptation here, and I just popped into my head momentarily, and then it went away, luckily. You're going to be doing some of these problems, and some of you might go, oh, dr dt. You might be thinking of related rates and throwing in those extra derivatives. That's not what we're doing. This is all with respect to r. The reason why we learned about factoring negative exponents is precisely for this situation. You want to always factor out negative exponents. I'm going to go out on a limb here and say that 4 must divide into 768. Yeah. 192 times. And I can factor out r to the negative 2 and be left with pi r cubed minus 192. And I need to double check that because my mind wandered for a second there. If I multiply that in, I get 4 pi r minus 768 r to the negative 2. It's fine. Okay. So in complete factored form, dA dr is equal to 4 times pi r cubed minus 192 over r squared. So we get 2 critical values of r. One of the critical values of r is 0, because that would make the derivative undefined. And don't discount that. I mean, I know it's not going to happen yet, but you need to think about, is it possible for that to be a solution? Because sometimes it will be. But it won't be in this case, because in this function, r must be positive. You cannot have a can with a 0 radius or a negative radius. R can be as big as you want. R can, in principle, be a kilometer. It's just that h is going to be a very tiny part of a millimeter. There's going to be nothing there. Well, something, but it's very small. So we're going to throw that one out. And the other critical value of x, or r rather, is the cube root of 192 over pi. And I did start today at some point saying I highly recommend not setting something equal to 0 on paper, but you might need to do that here. Even just writing it down like this, and then you go, oh, right, I'm going to add 192 and divide by pi and take the cube root. So since the second critical value of x, or r, is the only one that is in the domain, in high school, there's no need for you to do a first derivative chart. I can't speak to whatever program you're going to be in. They might have different expectations. So this r is actually the optimal r. What are we asked? What are the dimensions of the can? We're not asked for the surface area. We're just asked what are the dimensions. Well, we have r. How are we going to find h? We can go to our equation of constraint, which is that. And you know, at this level, I'll show you the exact value and what it will look like. But at this level, I'm trying to teach you the principles behind the math, not that kind of thing. So the height will be 384 over pi times the radius, which is this thing, squared. The radius is 192 over pi taken as a cube root, which is 192 to the third over pi to the third. When I square that, it's a power of a power, so I multiply that exponent of a third by 2. This 192 to the 2/3 can stay on the bottom. I have pi to the 1 over pi to the 2/3 on the bottom. So that's pi to the 1 minus 2/3. When you divide a common base, you subtract the exponents, so you get pi to the third. Which means the height is 384 over pi to the third, or the cube root of pi, times 192 to the 2/3. We could go on. We could see if we could write 384 in some kind of factored form and try to find a perfect cube that's in 192. I think 64 divides into 192. So you could start simplifying it, but that's good enough. I think maybe what we're truly interested in here is this. And the answer here is important because it's going to lead us to something I want to talk about. What is the radius approximately? 192 divided by pi, and I need to take the cube root. That's just how I take a cube root. You'll have to deal with it. I'm raising it to the third. It's about 3.9 centimeters in radius. And if memory serves, the height is going to be twice that, I think. Pretty close to twice that. I don't think it's exactly twice it. That's r. I need to take 384 divided by pi r squared. 7.9. And what's interesting here, man, I was sure I had a soup can. What's interesting here is when you look at the diameter of that can, which is twice the radius, it's about the same as the height. Nope. But, you know, when you get home today, go to the cupboard, grab a Campbell's soup can, just a regular one that's 384 mils, by the way. Pretty sure it's 384. Doesn't matter. They're not built that way. They're taller. Like the diameter of that can is not the height. It's taller than the diameter. And the reason for that is this is overly simplified. The cost of the material for the lid and the bottom are different than the cost for the sides. And if I told you that the cost per square centimeter of the top and the bottom was 1.5 times more than the cost per square centimeter for the side, we could do the problem again and build that in and get a more realistic answer. Anyway, that's the answer. That's a classic kind of max-min problem that you're expected to do in calculus. The final example, which I'm not going to do, we will do it tomorrow, is going to be a maximum area thing, which starts to include the idea that parts are more expensive than other parts, like the soup can could be. So this is saying, I'll just show this to you so that you can think about this. You're going to construct a building, a 4-sided building, along the shore of, I think it says Lake Fred, but the wall of the building facing the lake is going to be made of glass. Okay? And you want the area to be fixed. You need 200 square feet. The question is, what dimensions will minimize the cost if the glass is 3 times as expensive as the brick? It's more complicated. But we will tackle that one tomorrow. In the meantime, I think there's probably the odd question in here. This is not the only stuff. All of the questions from yesterday are still on the list, on the table. I'm sure there's going to be questions in here which maybe you can't do yet because you haven't seen the Lake Fred problem. But there are also going to be questions that you can do even though they're quite challenging. And I think my plan is to probably spend the remainder of the week doing max-min problems.